Okay, in this lecture we're going to cover the first part of our section 3.7 material on improper integrals. So let's recall briefly what we've been working with for definite integrals so far. So all of the definite integrals that we've been working with are defined for a continuous function f on a closed bounded interval from a to b. So thus far, all of the integrals that we've been working with are the integrals of continuous functions defined over some closed bounded interval. Now in this section, we are going to extend the definition of a definite integral to either discontinuous functions over an interval or unbounded intervals. Now these types of definite integrals are referred to as improper integrals, and there are two types of improper integrals that we're going to discuss. The first of which that we'll look at in this lecture is called type 1, and these would be integrals that are defined over an infinite interval. So we would say integrals where one or perhaps both of our limits of integration is infinite would be an improper integral of type 1. So there's three different cases that we could consider here. The first is if our function f of x is continuous on the unbounded interval from a to infinity, then we would define the integral of f of x over that infinite interval from a to infinity as the limit as t approaches infinity of the integral of f of x from a to t. So what we're doing here is we're looking at a definite integral of a function on some closed interval from, let's say, from a up to t, but then we're allowing the upper limit of integration t to approach infinity. And if this limit exists, that's how we would define the improper integral over the interval from a to infinity. So to illustrate this, what we're really doing here is the following geometrically. So let's say that we have in the xy plane the graph of some function y equals f of x, and it's continuous everywhere from x equals a all the way to x equals infinity. So it's continuous for all values greater than a. So the way that I'm defining this definite integral from a to infinity would be as the definite integral from a up to some value t. So we're looking at the area of this shaded region under the graph of f of x on the interval from a to t, and then we're allowing t to become larger and larger to infinity. So I'm going to add more and more area here. And that will be what I would define as this improper integral, provided that that limit exists. Now, in a similar way, we would say if the function f of x is continuous on the unbounded interval from negative infinity up to b, then we would define the improper integral of f of x over this unbounded interval from negative infinity up to b as the limit of the definite integral of f of x from t to b as t approaches negative infinity. So again, we're going to replace that infinite limit of integration with some variable, let's call it t, and then take the limit of that expression as t approaches negative infinity. So again, geometrically, what we're doing here is considering the graph of some function, say y equals f of x, which is continuous on the interval from negative infinity up until b. And I'm going to define that definite integral as the integral from some point t to some point b. So I'm looking at the area under the graph of my function on that interval, but then I'm allowing t to approach negative infinity. So as we decrease the value of t towards negative infinity, we keep getting more area. And as long as this limit exists, then that's how we will define this improper integral. Now the last case is if our function f of x is continuous on negative infinity to infinity. That is, it's continuous over the entire real line. So in this case, we would say that the improper integral of f of x over the entire real line from negative infinity to positive infinity would be found by taking the sum of the definite integral of f of x from negative infinity up to some point a, and then adding the improper integral of f of x from a to infinity. So to integrate over the entire real line, we would split the real line into two parts, everything from negative infinity up to some number a, and everything from a to positive infinity, and evaluate each of those improper integrals, and define the integral over the entire real line as the sum of those two values. So here, to illustrate, let's say that we have in the xy plane some function which is continuous over the entire real line. So if we want the improper integral from negative infinity to positive infinity, I'm going to consider the integral from negative infinity up to some value a, plus the integral from a to infinity, and each of these two integrals is improper, and we could evaluate them as they were defined in parts 1 and 2. We could take some limiting value, or some, say, arbitrary value t1, and look at the integral from t1 up to a, and some other value, let's say t2, and look at the integral from a up to t2, and then we would allow t2 to approach positive infinity, and we would allow t1 to approach negative infinity. And as long as both of those limits exist, that's how we would define the definite integral from negative to positive infinity. Now, some terminology that we're going to use when we're evaluating improper integrals is convergence or divergence. So let me introduce a definition at the bottom here. We would say that improper integrals are convergent if the limit exists. So all of these improper integrals are defined in terms of a limit. As long as this limit exists, we say that that improper integral is convergent. However, if the limit that we're using to evaluate these improper integrals does not exist, then that integral is said to be divergent. So when we're looking at improper integrals, we're asking the question, do they converge or do they diverge? And something to make note of in this third case of an infinite interval is that in order for the improper integral over the entire real line to converge, we need both integrals to be convergent. So when we split this integral over the entire real line into the sum of two parts, we need each of these parts to be convergent in order for that sum to be convergent. So now that we've discussed how to define improper integrals over an infinite interval, and we've introduced the terminology of convergence or divergence, let's look at some examples. So in this first problem, we're asked to evaluate each integral or show that it diverges. So in part A, we have the integral from 1 to infinity of 1 over x squared dx. So we recognize this as being an improper integral right away because our upper limit of integration is infinite. This is an unbounded interval from 1 to infinity. So here, in order to evaluate this, we would have to define this in terms of a limit. I'm going to take the integral from 1 to t of 1 over x squared dx, and then allow that upper limit of integration t to approach infinity by taking a limit. So let's see what we have here. We have the limit as t approaches infinity of, well, to integrate 1 over x squared, we would find an antiderivative, which would be negative 1 over x to the first power, and we're evaluating on the interval from 1 to t. So we have the limit as t approaches infinity of, when I evaluate this at x equals t, I would have negative 1 over t, and then I subtract what I get when I evaluate at x equals 1, which would be negative 1. So subtracting a negative 1 gives me a plus 1. And then in my last step, I would take the limit of this function as t approaches infinity. Now that first term, 1 over t, would decay to 0 as t gets larger, and I'm left with 1. So here I would say that this improper integral is convergent to a value of 1. So in part A, let's think about sort of what we just calculated, what this improper integral represents geometrically. So we were looking at the graph of 1 over x squared. So that looks something like this. From x equals 1 to infinity. So I'm looking at the area under this curve on the interval from 1 all the way out to infinity. And we see here, well, although x is increasing to infinity, that is, although we're adding more and more area, the area under the graph of this function is becoming smaller and smaller because the function is decreasing so rapidly. So here, the area of this region is given by 1 square unit as we've evaluated it, making use of this limit. Now in part B, we have a problem which is quite similar, the integral from 1 to infinity of 1 over the square root of x dx. So again, we recognize this as an improper integral since we have an unbounded interval from 1 to infinity. So as with part A, for these improper integrals, we have to make use of a limit. So I would be taking the limit as t approaches infinity of the integral from 1 to t of 1 over root x dx. So here, evaluating this, I would have the limit as t approaches infinity of, well, we've got 1 over square root of x, or x to the negative 1/2, which would have an antiderivative of x to the positive 1/2, or root x, divided by 1/2, which is equivalent to multiplying by 2. And we're evaluating from x equals 1 to t. So this would give us the limit as t approaches infinity of 2 times the square root of t minus, when I evaluate at x equals 1, I would have 2. And now as t becomes infinitely large, 2 times the square root of t becomes infinitely large. So this function is approaching infinity. We have an infinite limit. Our limit does not exist. It's not approaching any real number. So we would say that this integral is divergent, or if we want to be a little more clear, we could say that this improper integral diverges to positive infinity. Now, in part B, let's think about what this integral was representing geometrically. We were considering the area under the graph of a function, y equals 1 over the square root of x, which looks very similar to 1 over x squared. It's just not decreasing as rapidly. So on 1 to infinity, we're calculating the area under this curve, and although it does continue to decrease as x becomes larger and larger, it doesn't decrease as rapidly as the function in part A, 1 over x squared. So in this case, as we keep adding more and more area under the curve, we get a region that has infinite area. So this sort of raises the question, well, in parts A and B, we had very similar functions, 1 over x squared, or 1 over x to the 1/2 power. We saw that one of these integrals was convergent with a value of only 1, and the other integral was divergent. It approaches infinity. So the question is, well, what would be the magic value of, let's say, 1 over x to the p power? What is the number p at which we would see the difference between convergence or divergence? We saw here that if that power of x in the denominator was 2, we have convergence. However, if the power of x in the denominator was 1/2, we saw divergence. So it's somewhere between 2 and 1/2. And the answer to our question that we're posing about where that difference occurs is given by the following theorem. This is known as the p-test for improper integrals. And it says the following: if we have the improper integral of a function of the form 1 over x to the p power on some interval from a to infinity, where a is a positive number and p is a constant, then this integral will converge as long as the power p is greater than 1, and this integral will diverge if the power p is less than or equal to 1. So as some quick examples to illustrate the p-test, we could say, if we're integrating, let's say, from 2 to infinity, something of the form 1 over the cubed root of x dx, well, this would be the same as 1 over x to the 1/3 dx. And here our power of p in the denominator is less than 1. So we could say that this integral is going to be divergent. Now, if we considered another problem similar to this, let's say the integral from 3 to infinity of 1 over, let's say, the square root of x to the 5th power dx, well, that's the same as the integral from 3 to infinity of 1 over x to the 5/3 power. So in this example, our power p would be 5/3, which is greater than 1, which would mean that this integral converges. So this p-test for improper integrals allows us to quickly determine whether certain improper integrals will converge or diverge. Now, something that I want to stress here is that this p-test only holds for functions of the form 1 over x to the p on an infinite interval of the form a to infinity. So later in this section, when we consider other types of improper integrals which do not have an infinite interval, that p-test will no longer hold. So let's look at some other examples where we might not be able to immediately determine convergence or divergence using the p-test. So in this next problem, we're asked to evaluate each integral or show that it diverges. And in part A, we have the integral from e to infinity of 1 over x times natural log x dx. So when I look at this, I immediately recognize that this is an improper integral since my interval is unbounded. It goes from e all the way out to infinity. So in order to evaluate this, I have to use the definition of an improper integral. It's defined as the limit as t approaches infinity of the integral from e to t. So we're replacing the infinity in the upper limit by t and then taking a limit as t approaches infinity of this 1 over x times the natural log of x dx. So this is not a problem for which we could use the p-test because our function is 1 over x times log x. It doesn't have the form 1 over x to the p power because that log x term appears in the denominator. So instead, we have to evaluate this by finding an antiderivative of this function. And to integrate 1 over x log x, I could make use of a substitution. So let me choose u to be log x so that du would be 1 over x dx, or equivalently dx would equal x times du. So when I'm looking for the antiderivative of 1 over x log x dx, that would be the same as 1 over x times u, and then dx was x times du. So we see that a factor of x will cancel, and we're left with the integral of du over u, which is the natural log of the absolute value of u, where u was the natural log of x. So when we go back to our improper integral, we're looking at the limit as t approaches infinity, and this definite integral that we had is found by taking the antiderivative of this function, which we just found to be the natural log of the absolute value of the natural log of x, and we're evaluating this from e to t, and then taking our limit. So we have the limit as t approaches infinity of the natural log of the absolute value of natural log t minus the natural log of the absolute value of natural log e, which is 1. And we know that the natural log of 1 is 0. So we just have the limit as t approaches infinity of the natural log of natural log t. Now, as t becomes infinitely large, the natural log of t approaches infinity, increases without bound. So taking the natural log of this value, which is becoming infinitely large, would give us a limit of infinity. That is, there is no real number we're approaching. Our limit does not exist. So for part A, we would say that this improper integral is divergent, or diverges to positive infinity. All right. So let's look at another one. In part B, we have the integral from negative infinity to 0 of e to the 2x dx. So again, as soon as I look at this problem, I recognize this as an improper integral, since one of my limits of integration is infinite. We have an unbounded interval here. So in order to evaluate this integral, I have to make use of a limit. We would define this as the limit as t approaches negative infinity of the integral from t to 0 of e to the 2x dx. So that is the limit as t approaches negative infinity of, well, the antiderivative of e to the 2x is 1/2 e to the 2x from t to 0. So this gives us the limit as t approaches negative infinity of, when we evaluate at x equals 0, we have 1/2 e to the 0, which is 1, so 1/2, minus 1/2 e to the 2t, when we substitute t in for x. So now taking the limit as t approaches negative infinity, well, as t approaches negative infinity, this exponential term decays to 0, and we're left with just the 1/2 term. So here we would have an integral which is convergent to a value of 1/2. All right. So in our last one, we have in part C the integral from negative infinity to positive infinity of 1 over x squared plus 1 dx. So again, I recognize this as an improper integral right away because in this case, both of my limits of integration are infinite. So I've got an unbounded interval. Now in this case that both of our limits of integration were infinite, we said that we would have to evaluate this by splitting the integral into two pieces. First off, the integral from negative infinity up to some number a. So I can split this wherever I want. A typically good choice is to split the real line down the middle. Let's take everything from negative infinity to 0 first. And then add everything from 0 to positive infinity. So in general, we can split our integral wherever we want. Usually a good choice is 0. The only case where 0 might not be a good choice is if we have a integrand which is undefined at 0. So in this case, 1 over x squared plus 1, well, it is defined at x equals 0, so we would split our integral at that value. Now, in order to evaluate each of these two improper integrals, I have to make use of a limit. So for the first one, I would be taking the limit as t approaches negative infinity of the integral from t to 0 of 1 over x squared plus 1 dx. And then for my second integral, I would be taking the limit as t approaches positive infinity of the integral from 0 to t of 1 over x squared plus 1 dx. Now for each of these integrals, I know how to find the antiderivative of 1 over x squared plus 1. That is the arctangent of x function. For my first interval, I'm evaluating from t to 0 and then taking the limit as t approaches negative infinity. And for the second integral, I'm taking the limit as t approaches positive infinity of my antiderivative, which was arc tangent x, evaluated from 0 to t. So let's see what we have here. For the first part, we have the limit as t approaches negative infinity of arc tangent of 0, which is 0, minus arc tangent of t, and then we are adding the limit as t approaches infinity of arc tangent t minus the arc tangent of 0, which is 0. So simplifying just a little bit, I have the limit as t approaches negative infinity of negative arc tangent t plus the limit as t approaches positive infinity of arc tangent t. So let's see if we can evaluate these limiting values. Now, as t approaches negative infinity, the arctangent function approaches negative pi over 2. And since I had a constant of negative 1 out in front, I would have a negative of negative pi over 2, or plus pi over 2. And then I am adding the limit as t approaches positive infinity of arctangent t, which is pi over 2. So I have pi over 2 plus pi over 2, which would give me a value of pi. So we could say that this improper integral is convergent to a value of pi. Now, in the last step of this problem here, I was claiming these values of positive or negative pi over 2 for the limit of the arctangent t function. So how did I get those? Well, let's recall what the graph of the arctangent function looks like. So if we're considering the tangent function, we know that on the interval from negative pi over 2 up to positive pi over 2, our tangent function looks something like this. So to get the graph of the inverse function, recall that we take the graph of our original function and we would reflect around the line y equals x. So here my vertical asymptotes at negative pi over 2 and positive pi over 2 will become horizontal asymptotes at positive pi over 2 and negative pi over 2. And the graph of this arctangent function, well, reflecting the graph of tangent x about the line y equals x, we have the following graph for the arctangent function. So as we mentioned here, well, if t, or x, approaches positive infinity, we can see that our arctangent function is closing in on the horizontal asymptote positive pi over 2, whereas if t, or x, is approaching negative infinity, the graph of our arctangent function is closing in on this asymptote at negative pi over 2. But since we already had a negative in front of that arctangent function, this gives us a positive pi over 2 plus pi over 2, which is where that value of pi comes from.